Ladies and gentlemen, welcome to lecture number 24. At some point, I'm going to lose the number, to track the number. But anyway, I think this is lecture 24. So this will be the second lecture from chapter number 5. As you have seen, I told you last lecture what we're going to cover, and well, in this chapter. But in this lecture, I would like to I would like to get closer to the actual definition of the integral. And for me to do that, because I will need some kind of a sum, we need to talk about these sums, right? So in today's lecture, we will talk about the area as the limit of a sum, and you will see what kind of sum. You will see that I will try to approximate the area. So for example, if I'm given the graph of a function and I'm trying to approximate the area under the graph, you will see that I will use some kind of rectangles to approximate that. And you know, when you sum up the areas of those rectangles, it will give you something. So roughly speaking, this is what we're going to talk about today. And you will see that that area under the graph of a curve, well, by roughly approximates nothing else than the integral of that curve. All right, so let's get started. So first, I would like to start with some notation. Right, and before I even talk about the limit of a sum, I would like to see what is a sum all about. And you see, when I sum, I don't know, 6 numbers, I know how to do it, but when I sum n numbers, it will be a little bit tricky, and you need to maybe for the computation to be a little bit more to be easier, you need to use the notation for a sum. Anyway, we'll see what this is all about immediately. So when I'm talking about notation for a sum, this is what I mean about. So so the sum of n terms, let's say a1, a2, an, is written as that symbol over there that you see. It's called sigma, from the Greek letter sigma, right? And it says the following: sigma of ai with i going from 1 all the way to n. So in other words, it says sum all those ai's with i being indexed from 1, so starting from 1 all the way to n. So you add them up, a1 plus a2 plus an. So that's what you do, right? So this is the sigma. Let me write it here. So this guy is called sigma, is the Greek letter sigma. Well, as you have seen, we have used a bunch of Greek letters, and in mathematics, people like to do that. Sigma, alpha, beta, gamma, but you already know from the sorority, right? Because you use the same thing, if I remember right. Delta, pi, whatever. So I think you should, you know this kind of letter. So again, this is the letter sigma, and you sum up all ai's from I equals 1 to n. And let's see who these are. So I is the index of summation, right? ai is the ith term of the sum. And of course, the upper and the lower bounds of summation are 1 and n, respectively. So that's how we're going to write it. And now, so this is the general notation. I would like to see some examples. All right, so let's start with the example so that you can get accustomed with this notation, because we're going to use this notation for defining the integral. For example, let me start with the following example. Look at this baby right here. You see, you just sum up all i's from 1 to 6. So, and basically you just write them. It's 1 plus 2 plus 3 plus 4 plus 5 plus 6. Right? So sum of all i's from I being indexed from 1 to 6. So that's what you're going to do. What if I'm asking you, oh, let me ask you a similar question. For example, this one. What if I'm asking you this? What are you going to tell me here? Can you tell me? What does this represent, for example? So the sum of all I squared, right? All these numbers I squared from I being indexed from 2 all the way to 8. How can you tell me? How can we write this? What does this represent? Well, I'm all ears. So let's look at the sum. So what are the numbers that they're summing up? So are all the squares, right? And where do they start from? So they start from 2 and they end up at 8. So it will be what? It will be 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus, and the last one is 8 squared. You see, I start from 2 and I end up at 8. You see, I start from 2 and I end up at 8. But pay attention because I'm summing these kind of numbers, right? Does this make sense? All right, great. Let's see another example. Look at this one. This looks rough a bit, but it's not as rough as you think. So when I sum these numbers, 1 over n of k squared plus 1 from k equals 1 all the way to n, as you can see here, this term, 1 over n is a constant. So you see the index of summation is k. So let me point out this here. So the index of summation is k. So this guy here, 1 over n, so this guy here is the constant term in this sum. So if when you have a constant term, you take it out, great, and that's what we're going to do. So we can write in the following way. So let me do it here. So the sum from k equals 1 to n of 1 over n times k squared plus 1. So you're going to take out 1 over n. It's going to be 1 over n times the sum from k equals 1 to n of k squared plus 1. And now guess what? How can we write this sum here for this one here? You see it says like sum up all these numbers of this type from k equals 1 to n. Well, let's see, for k equals 1, what do we have? We have 1 squared plus 1. Great, you see it here. Look at it. For k equals 2, we have 2 squared plus 1. You see it here. For k equals 3, we have 3 squared plus 1. And the last one, because it's going all the way to n, from k equals 1 to n, the last one is n squared. You see, when k equals n, you see this is the last index, we have it here, n squared plus 1. And that's it. right? And then that's the sum. And then you factor 1 over n. If you want, you can factor 1 over n on the entire sum. So it's 1 over n times 1 squared plus 1 plus 2 squared plus 1 plus n squared plus 1. All right. I hope this makes sense. But anyway, we'll see plenty of examples today, so you'll dream about these sums tonight. Only sigmas you will see. All right, let's see another one. The third example. Look at this guy here. Let's look at the sum. So we would like to write the sum of all, to sum all these number f of xi delta x. So the sum from I equals 1 to all the way to n of f xi times delta x. You see, delta x is a constant term. So again, this guy here is a constant term. So since this is a constant term, we can take it out of the sum. And then we're left with, so this guy here, let's write it. So this guy here is nothing else than just delta x times the sum from k equals 1 to n of f of xi. And now we can only, if we write this guy here, look at this. So this will be, let's write it, this is delta x times, and now this is f of xi. So it means that sum all, wait, what am I writing there? This is not k here, this is I, I'm sorry, the index. Oops. Because it's I here, right? You see the index inside. So it means that this is f of x1 plus f of x2 plus f of xn, right? So this guy here inside is this guy here inside, right? They're equal, right? As we have C, right? Let's see, any questions so far about this? Is everything clear so far? I see silence, but okay, I see a question. All right. Exactly, yes, to any constant. Any constant in the sum, you take it out. Yes, that's what you do. You take it out, yes. Yes. Let's see, any other questions? All right, now let's let me tell you about the, we'll do some more experiments and I'll ask you, so don't worry about it. Let's see some summation formulas. Unfortunately, another thing that I hate is to tell you to memorize these sums, but anyway. These are the summation formulas that I would like to discuss with you. Well, they can be proven, but anyway. Usually when I learn about these formulas, well, they're discussed in, well, I learned them when I was a freshman in high school for the first time. And we discussed the induction principle. So they can be proven using the so-called induction principle. But anyway, I'm not going to go into that here. The only thing I can say is that just to, unfortunately, and I hate to say this, memorize them. Sorry about that. Let's see, the first one. So that's the second one, the third one, and the fourth one. Usually the first one, as you can see here, the sum over all constant c, and the sum goes from 1 to n, is c times n. And why is that? Let's see. Can somebody tell me why is that? So how can you write this sum here? This one here is what? Maybe you can take the constant out, take it out. So it's c times the sum from k equals a. No, is not, no. Is not 1 times c, 2 times c, 3 times c, because it's not k there. So it's only 1 here. So it means sum up 1, 1, 1, n times. So this is c times 1 plus 1 plus 1 plus, and we go all the way plus 1. How many times? Well, it says n times. That's what it is. So this would be 1 plus 1 plus 1 n times is n, is c times n. And there you go here. Right? Does this make sense? Also, Ehsan, is it clear now? And others? All right, great. Because I don't have an I there inside. So it's not like what you wanted is that if I have something like this, C times I, then yes, you could have said it's okay, I'm going to take, it's C, it's 1, C times 1 plus C times 2 plus C times n. Yes, I agree with that. So this is true, correct. All right, let's see the second one. So the second one is nothing else than the sum of the first positive integers, first n positive integers. Well, I already tell you the result, what it is, but I want you to tell me how can I, well, I already told you that, how can I write this? The sum from I equals 1 to n of I. So I'm summing up all these numbers I from 1 to n. How can I write this? Tell me. So this guy here is what? How can I write this? We sum up all i's from I equals 1 to n. How can I write this? From I equals 1, you have 1. From I, for I2, you have 2. So it's 1 plus 2 plus all the way till n, right? N is the last one. You see, it starts from 1 and ends up at n here. So that's the sum. So the sum of the, so this is nothing else than just summing up the first n positive integers. Guys, am I clear? So you're summing up all these numbers I from I equals 1 to n. So for I equals 1, it's 1. For I equals 2, it's 2. For I equals n is n. So you sum up all of them. 1 plus 2 plus n. And 1 plus 2 plus n will give you this guy here. So this is equal to this. N times n plus 1 over 2. All right. Tell me about this one now. This guy is what? What is it? The sum for from I equals 1 to n of I squared. How can I write this explicitly without the sigma notation? What is it?
1 squared plus 2 squared, etc.
Exactly. 1 squared plus 2 squared plus, which one is the last one?
And
n squared, right?
yes.
So, and I have here n times, right? So this guy here, like I said, this guy here, right, is this guy here. And also, what about the last one? So the last one, you can write it in the same way. So this guy is nothing else than just 1 cubed plus 2 cubed plus n cubed. And this guy is this guy. So the sum of the first n cubes of the first n, the cubes of the sum of the cubes of the first n positive integers is given by, as you can see, is nothing else than the square of the first sum. So this is this guy here. All right, so these are the sums, the summation formulas. In fact, I would like to dwell more on these three here. These are very important. Unfortunately, like I said, there is the proof is by induction. Anyway, there are also some other elementary proofs, but I don't want to deal with that because it will take some time. So that's what you need to know. Now let me write them again here before I, so the first one, let me write S1, I'm going to write it in this way, is the sum from k equals 1 to n of, or let me stick to the notation with I. So the sum from I equals 1 to n of I, which is 1 plus 2 plus n, and this is n times n plus 1 over 2, everything over 2. S2, the second sum is the sum from I equals 1 to n of I squared, which is 1 squared plus 2 squared plus n squared, and this is n times n plus 1 plus times 2n plus 1, everything over 6. And then the last one, let me write it somewhere here. S3, which is here, is 1 cubed, well, let me write, is the sum from I equals 1 to n of I cubed, which is 1 cubed plus 2 cubed plus all the way plus n cubed, which is nothing else than just n squared times n plus 1 squared, everything over 4. Or if you want to write it in this way, you can write it as n times n plus 1, everything over 2, and everything squared here. Oops. All right, so these are the three sums that you need to know, right? And like I said, the proof can be done by induction, but I don't want to get into it. In fact, we will make use of these three sums. It will turn out that they will be very important. But before we go there, let's do an experiment. So let me ask you something, like this innocent question. So let's start with the following experiment. So consider a particle that moves at 5 feet per second for 3 seconds. How far does it go? Let me get some water. I'll be right back. $15, right? How did you do it? Why is it 15? Exactly. So in other words, the distance is the rate times the time, right? So so the distance, the rate is 5 feet per second times the time, which is 3 seconds, so it's 15 feet. Great. All right. Let me ask you another question. So this is question 1. So let's keep track of them. Let me ask you another one. Question 2. Now, suppose the particle moves 5 feet per second for 1 second, then 3 feet per second for 2 seconds. How far does it go? Hmm. 11. And why is that? Why is that, Jonathan? So, exactly. So it's rate 1 times time 1 plus rate 2 times time. Exactly. Great. Beautiful. So in other words, the distance again is the rate times time, but as you can see, we have the rate is something for one time, and the rate is something else for the second time. So just like Jonathan put it perfectly, so it's the first rate, let's here rate 1, times time 1, and here is rate 2 times time 2. So it's 5 times 1 plus 3 times 2, which is 11. All right, great, beautiful. Now, let's see something else. Let's go a bit further. So let's see question number 3. What about this one? Next, suppose the particle moves 5 feet per second for 1 second, then 8 feet per second for 1 second, then 3 feet per second for 1 second. Oh, how far does it go? Exactly, 16. So again, this will be rate 1 times time 1. This is rate 2 times time 2. And this is rate 3 times time 3. So we're going to add up these three. So the distance is rate times time, and of course, it will be 16. So it's 8 times 1 plus, well, I should have said times 5 times 1 plus 8 times 1 plus 3 times 1, which is 16, right? All right, great. Let's extend our experiment a bit. Look at this one. Now, suppose a particle is moving with velocity t squared plus 1 from t equals 0 to t equals 3 seconds. How far does it go? I want you to see here. You see, the velocity is also variable. So the particle is moving with velocity t squared plus 1. So the velocity v of t is t squared plus 1. From t equals 0 to t equals 3 seconds. So how far does it go? So what do you think? You see the difference? So this is, let's say, question 4. Let's go back to question 3. See, here the situation is clear. It says 5 feet per second for 1 second, then something else for 1 second, then something else for 1 second. Here it says it's variable. As the particle is moving with velocity t squared plus 1 from t equals 0 to 3. So if we say the same thing, the distance is rate times time, but it doesn't really help, right? So we cannot say the same thing. So that's why here where we're gonna need to do something else. You see, the situation will get a little bit more complicated. And that's why we need integration. And well, anyway, we'll go there. So let's break this into pieces, because you see the time there goes from 0 to 3. So maybe we should divide this time in some way. You see the time, this t here is between 0 and 3. And t is variable, it can be anything, can be 0.1, whatever. So maybe we should break this into pieces, just like I said. So let's divide. So what we're going to do is the following. We're going to divide the interval from 0 to 3 into small pieces. And we can do this in a very nice way. Oh, God. I don't know, I think I got cold or something. I don't think it's COVID again, but you never know. So, just like I said, we divide this from 0 to 1, then from 1 to 2, and then from 2 to 3. You see delta t, so the difference will stay the same, and that will be great. So you see delta t, which is, it's 1 second, right? The difference of 1 minus 0 is 1, 2 minus 1 is 1, 3 minus 2 is 1. So delta t is 1 second. And now let's do something. Let's pretend that the speed, and by the way, the speed is different than the velocity. Now let's pretend for a second that the speed is constant. So that's what we're going to do. So recall the velocity is this function, just like I said, v of t is t squared plus 1. Well, let's see, when t equals 0, it's quite clear that the speed is 1 feet per second. Well, the velocity, not the speed, sorry. Here's the velocity. When t equals 1, guess what? You're going to plug in t equals 1, the same thing. The velocity is 2. It's 1 squared plus 1, which is 2 feet per second. And then when t equals 2, the velocity will be 2 squared plus 1, which is 5. Great. And now let's pretend that that the speed, not the velocity, doesn't change on each time interval of length 1, right? So when we are from 0 to 1, it doesn't change. From 1 to 2, it doesn't change, and from 2 to 3, it doesn't change. So we'll pretend that the speed is constant. So I messed up here with velocity and speed, but anyway. So let's use an old formula on each piece. So let's do that. Again, between 0 and 1 seconds, we can multiply, right? V of 1 times delta t, which is 1, right? Look here, V of 1, which is delta t, V of 0, sorry. V0 times delta t, but V0 is 1, so it's 1 times 1, which is 1. And you see it here. Then between 1 and 2 seconds, we see that at the 1 was 2, so it was 2, so V of 1 times, again, delta t, which is constant, so this will be 2 times 1, which is 2, and you find it here. And then the last one if we want to measure the distance between 2 and when t is between 2 and 3 seconds, then as you can see, this is v of 2 here, which is 5 times 1 times delta t here. So it's 5 times 1, which is 5. And you see it here. Wow, great. So we have this. So now let's see the total distance. So we would like to, when we would like to find the total distance, we would like to add up all these pieces. So we're going to add up all of them. So add up the pieces. So the total distance would be v of t, the sum of v of t, which is 1 plus 2 plus 5 times the 1, right? This guy is 1. So this is nothing other than just the sum, so summation of v of t. And I'm just going to use this generically because this will be nothing other than just v. In fact, it will be from t equals, well, I cannot say from t equals 0 to, okay, let me say it, from t equals 0 to 2. T. So this is v of 0 plus v of 1 plus v of 2. V of 0 is here. V of 1 is here, V of 2 is here. So when you add this up, it will give you 8 feet. Let me tell you something. This is a very crude approximation. Don't you feel like it? Because we tried to mimic the same thing as we did previously, right? But we tried to break into pieces. So, you see, this is why you need integrals in your life. Again, let's go back to see what did we do here. Let's go back to our question because I want you to see this is a very important moment. You see, now the particle is moving with some velocity, and the velocity is given by this quadratic function t squared plus 1, and t goes, the time t goes from 0 all the way to 3. And we would like to see how far does it go. So we'd like to answer the same question. Oh my. Oh my. All right, let's see. There's a question. All right. I see something here. Oh, you're going too far. Yes, Jonathan, you're right. So Jonathan asks, so we can take the antiderivative of the velocity to get the position formula. Yes, I totally agree with you on that, but I'm trying to mimic it like from scratch. I want to do everything from scratch, not just to, you know what you're doing right now? You're killing the mosquito with the atomic bomb. So that's what you're doing. So, which is, yeah, it's in a very efficient way to finish up of the problem. But I'm trying to do it from scratch because I would like to use the approximation of the integrals. But anyway, yes, you're right, Jonathan. I agree with you. But you see, this is a very crude approximation what we said. So what did we do here? So we knew that t is from 0 to 3. So we said, like, let's break this into pieces. So let's say t, in fact, let me write it in this way. So I have this line here. So this is from 0 all the way to 3. And we say, let's break into pieces. 1, let's say here we have 2, and from 2 to 3. And let's see what happens here when t is here. Then let's see what happens here and then here. And then that's what we did. We said that the delta t is, for example, delta t here is constant, is 1. Here's 1, sorry. So great. And then we just use the same type of formula. And we ended up with the total distance. So we computed the distance on each sub-interval from 0 to 1, then from 1 to 2, and then from 2 to 3. But then we ended up with, when we computed the total distance, we added up these pieces, and we end up with 8. But let me tell you, this is a very crude approximation, and you will see why. How far is this very intuitive? Because this is how you intuitively would do it, right? You'll be like, okay, let me break into pieces and let me see what happens on each piece. And those pieces such that the speed is constant on each. So, but still it's not enough. Let's see. So there we go. The big idea of integration, finally, we're here. That's why you need integrals in your life. Trust me, you will use them. If you want to be like a hardcore engineer or, I don't know, hardcore chemist. I don't know if you want to be a hardcore biologist, you'll use integrals, but I can definitely tell you that as a chemist or engineer, you'll use these integrals. So let's see what this is all about. So as you can see, based on our previous experiments, something happened. So first, something was changing, so we couldn't use the old algebra formulas, right? Also, a second thing was that when you break the interval of independent variable into pieces, that's a little bit too much to do. And then when we did this, we pretend everything is constant on each piece, right? And then we added up the pieces. And that's what it is called the Riemann sum, and I didn't tell you. So that's what we did. And we said that when we add up those 3 pieces, that's it. Remember when we added up these those pieces, it was this sum here, right? Of f of t times delta t. Well, in our case, with the velocity, it was v of t. So that's what we call the Riemann sum. So this is the Riemann sum. But anyway, I'll explain a bit even more. Well, if we use more and more pieces, the limit is the right answer. So this limit is a definite integral. In other words, just like Jonathan said directly, is nothing else than just the integral of v of t dt. So in our case, we will try to approximate that sum, that finite sum, with the integral. Since t was from was in interval 0, 3, so we will try to approximate this sum, this Riemann sum, with the integral from 0 to 3 of f of t dt. Well, in our case, this was v, because that was the velocity function. Wow, that was the big idea of Riemann. Can you believe this was not even known till like 140, 50 years ago? Well, yeah, 150, 160 years ago. It was not even known, all this stuff. It's so natural. But anyway, this is how mathematics is. So these are the big ideas of integration. So we'll, instead of summing up all those pieces, maybe we should just take the integral, especially when the movement, the movement of the particle is not described, is not like a rectilinear movement. So maybe it's some kind of, God knows what it is. So this is where the integration comes into play. All right, great. All right, let me start with something basic. Let me remind you something. You see, If I give you a rectangle, as you can see in this picture, this blue rectangle, what is the area? So the area is the height times the width, right? Right, this is the height here. This is the width here, right? So you multiply these two, and then you get the area of the rectangle. All right, great. So that's the ideal scenario, but like I said, something worse can happen. So what happens if I have a curve? Look at this. And let me stick to this curve here. So the simplest parabola, as you can see, I take the curve. Look at this beauty here. Y equals x squared. Right? And I'm interested from zero, from here, starting from zero here, all the way to 1 here. What is the area under the curve? Look. I'm interested about this area here. So what is the area under the curve of this yellow portion here? So for you, how can we do this? Maybe I'll try to approximate this by, I don't know, maybe it is like height times width. But, you know, that doesn't help much, unfortunately. So, because we can ask one simple question. What if the height is changing? What can we do? Right? So what if the height is changing? Well, if the height is changing, then the area is not the height times the width, so it doesn't help that much. But maybe we can do something. Maybe we can approximate this by some kind of rectangle. Oh my, by some kind of rectangles. And let's see. So let me explain this. So I want you to look at this picture. You see, so I'm considering this function. So f of x is x squared on 0, 1, right? And what I'm going to do is the following. So I'm going to divide the interval 0, 1 into 5 subintervals of equal length. I want you to pay attention. So I'm going to divide the interval 0, 1 from 0 to 0.0 to 0.1, then from 0.1 to 0. No, into 5, okay. From 0 to 0.2, then from 0.2 to 0.4, then from 0.4 to 0.6, then from 0.6 to 0.8, and then from the fifth interval will be from 0.8 to 1. Great. So the endpoints and also the length of each interval is 0.2 minus 0, which is 0.2. Then the length of the second interval, subinterval, is 0.4 minus 0.2, which is again 0.2. I want them to divide into 5 subintervals of equal length. And this, I should stress this one out here. So the length of the intervals will be delta x, and this guy is here. So let me write again, delta x, it's 0.2. All right, great. So the endpoints, so do not forget that this is the graph of my function f of x. So this, oops, look, this is my curve here, so it goes all the way up. And I'm trying to approximate this area here. So please do not forget, this is my goal here. I'm trying to approximate this area here. The area under the graph of f, right? This area. All right, so what I'm going to do first, just like I said, I'm trying to divide this interval 0, 1, because it started all the way from 0 and it goes, this is 0 here. It goes all the way to 1 here. So what I'm going to do is just going to divide this into, like I said, into 5 intervals of equal length. All right, so that's the area under the graph. All right, and like I said, the endpoints on H will be 0, then 0.1. Well, we can denote this by x0 is 0, x1 is 0.2, then x2 is 0.4, then x3 is 0.6, x4 is 0.8, and x5 is 1. So let me write them here. So this is x0, that's the next one, x2, x3, x4, and x5. All right, great. And now, if we pick each subinterval, right, on each subinterval xk minus 1 xk, we consider a rectangle with height the value of the function on the right endpoint. And look here. Look at these rectangles here. What can I use? All right, let me go with this one. Look at this rectangle here. Right? So this is the, look at this one here. And also look at this one here. And again, this one here. Let me denote this by, and also this guy here. So we can approximate this so by this. But you see there is a lot of like extra area. But anyway, we can approximate this by rectangles. And let me do it like this so that you can see the actual rectangles, you see. And like I said, the height of each rectangle is the value of the function at the right endpoint. And let's see, how can we do this? You see, let's see if, how many rectangles are there? Can you tell me? 1, 2, 3, 4, 5. 5 of them, right? And we'd like to compute the area of each one of them. Great. So let's do that. So the total area will be 5 rectangles. As you can see, I'm not quite yes, it's the area under the graph. It's included in the areas of the sum of all rectangles. So as you can see, it's not the best approximation, but it can be something closer to it. Anyway, so the total area will be given by these 5 rectangles, right? So this will be, let's denote this by S5, will be the sum from k equals 1 to 5 of f of x k times delta x. Let's see. Who is f of, so this guy here, let me just say it again. So this guy here is f of x1 times delta x by using this, plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x plus the last one, f of x5 times delta x. Great, beautiful. All right. So what is f of x1? Can you tell me? Because we said. So f of x1, keep in mind that f of x is x squared. And x1 is what? You see it here, is 0.2, x2 is 0.4, then x3 is 0.6, then this guy is 0.8, and this guy is 1. So we have to compute f of 0.2. So f of x2 is f of 0.2, f of x3 is f of 0.4, f of x 4 is f of point. Wait, where am I? All right, I just give me a second. So f of x1, sorry. So f of x1 is f of 0.2. F of x2 will be f of 0.4. F of x3 will be f of 0.6. F of x4 will be f of 0.8. F of x5 is f of 1. So we have to compute these numbers. So let's do that. And then keep in mind that delta x is this guy here. So we're going to multiply by 0.2. So this sum will be, well, we just f of 0.2 is, since f of x is x squared, it's 0.2 squared plus 0.4 squared. Because here, this sum, you can just factor delta x, and it will be times the sum from k equals 1 to 5, sorry, of f of xk. So that's delta x here. Now you're going to, f of x1 is 0.2 squared, f of x2 is 0.4 squared, and so on. And then guess what? When you do the algebra, and when you can trust me, you can check this by with a calculator, you will end up with 0.44. So the area under the graph of the function f of x equals x squared when x goes from 0 to 1 is 0.44. All right. So this is the approximation of just using 5 rectangles. What do you think? The more I take, if I take more rectangles, do you think I'll get a better approximation? What do you think? Yes, your intuition will say yes. Well, if you take a large number of rectangles, you'll get a much better approximation. So as you can see, if I take more rectangles, let me show you this picture. Look, you see, we dealt with this scenario here. So this is what we did. So the area was under the graph was 0.44. So we dealt with this one, but you can take more rectangles here, as you can see, right? And so here are more rectangles, right? How many of them are there? Like 1, 2, 3, 4, 5, 6, 7, 16, right? And God knows how many are here. So you see, you get a much better approximation. So here we get a much better approximation. Great. So now I think I explained the general idea without even saying it. What if we take, instead of taking, we take n rectangles. So in other words, we divide, let's say, the interval 0, 1 into n subintervals of equal length. So let's do that. So what are we going to get? Let me explain this. So divide the interval 0, 1. So we're going to take the closed interval 0, 1. Right? And we're going to divide this into n subintervals of equal length. Well, the length of each subinterval is, well, if you divide this into n subintervals, it's, let me just draw a picture. So let's just say we have this interval from 0 to 1 here. So you get 0, 0. So it's 0 to 1 over n, then 1 over n to 2 over n, then 2 over n to 3 over n, and so on. Then you get, let's say here, k minus 1 over n, k over n, and so on. The last one will be n minus 1 over n to n over n, which is 1. And this is why, if you like, 0 is 0 over n. You see? So these are n subintervals of equal length. So delta x, if you want, on each one of them, so this is delta x, the same goes here, delta x, because the length, well, you subtract the endpoints, right? So 1 over n minus 0 is 1 over n, then 2 over n minus 1 over n is 1 over n, and so on. And if you look here, this will be, this is the kth subinterval here. So this is the kth subinterval, right? And of course, delta x is the same as k over n minus k minus 1 over n. And this is 1 over n. Great. And let's do the same procedure. So let's do the same thing as we did with those 5 rectangles. So by doing the same thing, so by taking as high the value of f on the right endpoints, right? Then guess what? The total area of each rectangle will be what? Will be the height times the width. So the area of each rectangle is what? Is f of, so f of k over n times 1 over n, right? And we're going to sum up all of them. So that's what we're going to have. So we're going to have the total area of those n rectangles. So let me point out, this is the area of the kth rectangle. So we have the first rectangle all the way to the nth rectangle. So we're going to sum up all of them, all those areas, and then guess what? By just writing it, we're going to end up with this thing here. And now we can actually compute this. We can factor, you see, this guy here, let me just write it. So this beauty here is the following. So I'm going to take another, as you can see here, this is 1 over n. Let me write it here. So it's 1 over n times 1 squared over n squared plus 2 squared over n squared plus n squared over n squared. And you can take 1 over n squared, a factor here, so it's 1 over n times 1 over n squared times 1 squared plus 2 squared plus n squared. And that's what we're going to do. And this guy here is nothing else, it's just 1 over n times 1 over n squared is 1 over n cubed times the sum of k squared. From k going from 1 to n, but we know this, right? This guy here is n times n plus 1 plus 2n plus 1 over 6, like I said previously. So we're going to end up with this number here. Ouch. Right? And then, guess what? What do you think? Do you think it's a good approximation for the integral? For the area? What do you think? Should we stop here? What does your intuition tell you? I can't hear you. Did you say anything? Well, maybe we should take n large enough. So the question is, what happens when n is large enough? In other words, as n approaches infinity. Well, you can write this in this way as well. And as n approaches infinity, can you tell me this will approach what? What do you think? This will approach what? As n approaches infinity. 1 over n approaches what? Approaches 0, right? So the limit will be 1 over 6 times 1 plus 0 times 2 plus 0. So in other words, it will be, so the lim as n approaches infinity of Sn will be the lim as n approaches infinity of 1 over 6 times 1 plus 1 over n times 2 plus 1 over n, which will be 1 over 6 times 1 plus 0 times 2 plus 0. It will be 2 over 6, which is 1/3. And there you go. So that's the area under the graph. So we did all this just to, just to find that the limit is 1/3. So that's the area under the graph. So we did it the hard way. Whew. So in other words, let me put it this way. So the area is the limit of the sum. So we go back at the title of our lecture, and we can say the following. If I have a continuous function, and let's say a continuous non-negative function on and the f is defined on an interval AB, we can say that the area bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is nothing else than just this beautiful sum that you see here. So it's the area is the limit as delta x approaches 0 of the sum from k equals 1 to n of f of a plus k times delta x, where delta x is nothing else than the length of each subinterval, right? Which is b minus a over n. In other words, you can write this in the following way. So this can be written as the lim as n approaches infinity of b minus a over n times the sum from k equals 1 to n of f of a plus k times b minus a over n, right? And this guy here is nothing else. I'll tell you in advance, it's a big surprise, but probably you expect is nothing else than just the integral from a to b of f of x dx. So that was the amazing idea of Riemann. Beautiful, amazing. So Riemann was a German mathematician. I think he died of tuberculosis at the very young age. I think he was 39 or 40. But basically, his contributions to mathematics were, I don't know how to call them. But in other words, he changed the face of mathematics forever, which he wrote only 6 papers in his life, but each paper of his was like a enormous contribution to mathematics. In other words, he changed the face of mathematics. Well, one of the things that he did was this one, the Riemann sum, so expressing the integrals as the sum of areas of rectangles. Since, well, people kind of knew how to compute integrals, but he was the one who actually put the foundations to this. All right, I think in the remaining time, since let's see how much time I have left, not much probably. You can do the same thing. No way. So there's a question here from Brian. Do you think we discovered everything about math? No, not even close. We know very little about mathematics. For me, mathematics is like God. So there's no way you can know everything. Because you can express everything in, this is how they say, right? Mathematics is the universal language. You can express everything you can say in nature. You can see in nature in terms of some mathematical objects. Exactly. So there are like millennia, like Cameron says, there are 8 millennium problems, big conjectures. And one of them is so-called the Riemann Hypothesis. So it's again related to Riemann. It's another major contribution of his. And we still don't know what happens to the zeros of some function, Riemann zeta function, whatever. You'll learn about it a bit in calculus too, but for real exponents. The question, the conjecture is about the complex, the non-trivial complex zeros of that function. Anyway, not getting into detail. Well, now in the remaining time, I would like you as a homework to do the same thing. So this will be a homework for you. So I want you to do the same thing, to use a summation definition of the area. So you're going to go in the same fashion to find the area under the curve y equals x cubed on 0, 1. And then guess what? You're going to divide, well, in this case, it will be simple. In fact, let me just tell you. Because you're going to divide the interval, again, into, in fact, let me just say it. You're going to divide, again, the interval into n subintervals of equal length. And of course, you can compute f, well, delta x will be 1 over n, right? And then you compute a plus k times delta x, which is k over n. And then you form the Riemann sum. And then the area is given by this here. And then you do the same thing. You're going to, but this time, you're going to use this guy, which is 1, the first of the n cubes. And you know a formula for this, which is given by this. And then you're going to take the limit as n approaches infinity and so on. Anyway, I'm going to leave the details to you. And one last thing is I would like to address this question. So how does this area, right, which is given by this limit, change when we use left endpoints? That's a question. Well, the answer is simple. It's going to change just like this. But when you take the limit as n approaches infinity, you won't have a problem. All right. I think I'm going to stop here. Feel free to stop by my office hours in like 8 minutes if you have any other questions. And I guess I'll see you on Monday. Take care. I'll see you. Bye-bye.